Please give me 100% right now. I need someone nice to read the question. Or someone mean, doesn't matter.
A ball is held above the ground and then it is dropped so it falls straight down. Limit your analysis to the ball moving in the air before it hits the ground.
Okay, one more time because there's a lot of subtle things in there.
The ball is held above the ground and then it's dropped so it falls straight down. Limit your analysis to the ball moving in the air before it hits the ground.
Okay. I suppose that a really important thing that physics can do is help you develop imagination, okay, which TV probably destroys. I thought that was funny. Anyway, imagine dropping something and it hits the ground, right? You guys good? So, only worry about these two moments in time first. Forget that one for now. Are you guys good? Okay? Everybody good so far? So here's how every energy problem, every energy flow diagram works. You have energy stored in the first moment. So I'm going to call this moment in time A. These are the subtle kind of things that most people miss. And then energy never makes sense. Okay? If you get this, I think it'll make sense. Moment in time A. And then you got moment in time B. Everybody good so far? I heard nothing. Everybody good so far? Clearly, these are moments in time. In the Energy Skate Park Lab, the equivalent would be if you pressed what button? What would this moment in time be? You press what button to get a moment in time? You would have to press pause, and the bar graphs are at some spot. Does this make sense? Okay, same with that moment in time. In the middle is a duration of time. In other words, it's a time period. Does that make any sense? You guys good there? So you have a time period between moment in time A and moment in time B. Moment in time A, I'm just going to draw as best I can. And I'm going to write down some of the details. Okay? Is the object moving yet? That's one of the key questions. Is the object moving at this moment? At moment A. What do you guys think?
No.
So this requires imagination, right? Your object actually, at the moment you let go, at that instant your hand is no longer touching the ball. How fast is it going? That's the idea. Is it's not moving yet because it is accelerating. You're not holding it. The force due to gravity is making it accelerate 10 meters per second faster speed each second, but the velocity, the speed hasn't changed yet. It's zero at the very first instant. So that's what moment in time A needs to be. You guys good? Do you see how this simplifies our energy equation? Your energy equation for that moment in time is going to be EK plus EG plus E elastic. Are these the three that you're going to worry about in this class? Nature has many more places to store energy, but these are the only three you have to worry about. You guys good? So, since the velocity is zero at this moment, tell me, what's EK? Notice I'm getting rid of the easy, stupid stuff first. Is there any rubber band, bungee cord, trampoline, or is the ball made of rubber? Is there any indication that we're going to have energy stored in elastic? There's no elastic molecules mentioned here. There's no spring. Make sense? So this is also zero. So I'm just simplifying the problem and getting all the easiest stuff done. I'm going to do the same thing over here now. So I'm looking at the moment in time in the beginning, moment in time in the end. Okay? And the end for us now is position B, so I'm going to draw it. So drawing it is actually a critical step. So this is my height h, this is my height h, and it looks like the ball has fallen less than halfway, right? It's not halfway yet. So if that was h, I'm going to draw it like there. It's got to be moving, so I'm going to say v is greater than 0. Are you guys good? Okay, and then I'm going to copy the same terms here over here. I got EK plus EG plus E elastic. Everybody good? Which one of these is 0 in the end at position B, at moment B? Everybody. Is it moving? So it's kinetic 0. Good. Is EG 0? Okay. So elastic in this whole problem we don't have to worry about. Good. At this point, let's ditch this part and just erase it so we don't even have to look at it. Because this isn't part of our energy flow diagram. Everybody cool so far? Oh, that didn't work. There. Okay. Cool bananas? So in the middle, we draw a circle and we identify our system. And again, I gotta highlight this because this is a really important idea. This is a moment in time. This is another moment in time. Between is a duration of time. In other words, it's a time period. Maybe this is like 10 seconds it takes the ball to go from moment in time A to moment in time B. It could be any amount of time. Are you guys good there? So from this moment to this moment, is energy going to be lost from our system? And what is our system? You always have to choose what's your system. What do you guys think makes the problem simplest? There's a lot of ways to look at it. Is the ball going to be part of our system? The ball needs to be, simply because we won't have E kinetic here if we don't have the ball. The ball is what's moving. Cool? So that has to be part of our system. Anything else have to be? Gravity field. Very good. You would not have gravitational potential energy if you didn't have a gravity field that the ball is located in, right? So the good idea. I'm thinking that the simplest system that fulfills the requirements of EG and EK and the elastic, I'm thinking that's going to be the best system to choose. The bigger your system, the more complicated your system. The smaller your system, the more easy it is, right? So this is the smallest we can make it and still incorporate these. You guys good? Because these are the energy stored in our system. And this is the energy stored in our system at a different moment later. Okay, so now it's a matter of making up a number of blocks that you want to play with. How many blocks do you want to play with? Okay, you can do 4. Just to be a punk, I'm going to do 2, 4. Oh, that didn't work very well. All right, I'll do 6. And I'll write the number 6 here. Down below, I'm writing it my equation. What do I write for this? Plus 6 plus, what do I write here? So, you realize later, EK is going to be an equation. EG is going to be an equation. E elastic is going to be an equation. So it's going to get far worse, right? But not that bad. So you'll have equations for these terms. Cool banana? Are all these 6 blocks going to stay in our system? Where do you think they're going to go? Or some will go? Or how many will go? How many do you want to lose? 2? Why 2? Where are these? Where is energy going to go if it's going to leave your system? This is a key question. Our key question is, where is energy stored? How does it transfer? You guys good? So essentially, you're just accounting for your energy. Where do you think it's going to go? I'm hearing air resistance. What do you think? Now, we don't say air resistance here. We have a term that counts for air. You got it. What did you say? I'll write it again here. We say dissipated energy. And what are we talking about? Could be heat. There's a lot of things this could be. What was I going to say? The reason we call it dissipated energy is it easy to get it back to EG or EK or elastic? Why? You're talking air resistance. So would you folks agree that this ball traveled through the air and bumped into air molecules? Yeah. Okay, were those air molecules, their motion was disturbed and they hit other air molecules, right? And they essentially, all the air molecules within this region that were in the way of the ball would be moving a little faster as a result of the ball hitting them, right? So essentially, this is energy that's transferred out of our system to little molecules around the ball. You guys get the idea? And you see now the meaning of dissipated energy. It's not lost, but it's not easily retrieved back to EG, EK, or E elastic. We can't get it back into our bank account. You with me? It's kind of like this. You got $6 in the bank, right? Beginning of the month. Then you lose $1. They tax you, or they give you some fees and stuff for bouncing checks or whatever they want to give you fees for, right? So you lose $1. Then at the end of the month, you got $5 left. You get what I'm saying? That's the overall logic between these problems. You good? So let's just lose one, keep life simple right now. Everybody good? Okay, how do I distribute what's left? Let me do this part of the equation. Minus E dis, we lost 1, so I'll draw 1 block down here, and I'll say minus 1 for my equation. Now, here I'm going to put an equal sign, because the money in the bank in the end has to equal the money we had minus the money we lost, right? Does that make sense fundamentally? Okay. Okay, so where do I distribute my blocks now? Okay, he's suggesting 5 blocks there. EK. There's a problem with that. Do we have EG? And I'm going to give you an argument that will help, I believe. Has the ball fallen half its distance yet? So we got no business losing even half of our blocks. We need to lose only, if we said 3 blocks to EG, we would still be wrong because we haven't fallen half our distance. You see the issue? So could we use 4 blocks? Would that make sense? So if we put 4 blocks here, that's reasonable because we got a little more than half what we started and we're a little more than half our original height. You guys good? Cool? So there's logic there that you'll have to think about. How much left in EK? Is it 1 or 2? So if you can answer that question, if you're correct that it's 1, if you can figure that out, you're getting the idea. So let me just check you out. Is this correct? We got 6, we lost 1, now we got 1 plus 4, we good. We've done half the problem. Now, you've done energy flow diagram for moment B. You should probably copy it directly. So I'm just going to clone it, save a little time that way. Oh, that was beautiful. Try that again. Thank you. See how it takes a while for the computer to respond? It's low in memory. I don't know why. I deleted a bunch of files. I deleted like 70 gigs, dude. Clone that. And they're all video files of really annoying voice, really annoying face. All right. Everybody cool so far? You see what I did, right? I just copied B. Is our system going to change in any way? I'll ask that again. What's our system still going to be then?
The ball and gravitation.
Good. Thank you. All right. I don't know where I'm at now. I got lost. It's still moving up. This is fun. There we go. Just coming around soon. Isn't that cool? Oh, it went too far. No, that's good. You guys good? All right.
Now I'm gonna put my bit, see?
Yeah. I was just going to ask you folks, what's the system again?
Ball and gravitation.
Thank you. So ball and GF. You can write GF. I'll know what you mean. Now, position C, or moment in time C. Tell me, where is the ball exactly? I'm not saying this to be picky. I'm saying this because for you to really understand physics, you got to be aware of some of the subtleties. Okay?
Right before it set up.
Okay, what do you mean right before it hits the ground? Imagine this.
It's like a
How close is the ball to the ground?
really close.
How close is super close?
Like
Maximum what? Good. You are thinking correctly. This is good. Why would we choose this exact moment in time? And I'm gonna move this down a little. I'm gonna move that down just to illustrate that has the ball hit the ground yet? This is important, right? So the velocity is max, you said. This is the minimum height in this problem, right? So I should probably make a note of that. Minimum height. All right, I'll copy these over. EG, EK plus EG plus E elastic. Everybody get it? Now what? We lost 1. We didn't fall even half the distance. How much should we lose now? We got 5 to play with. Well, from A to B, how many did we lose to E dis and how far did we fall? So we fell a third of the way down. We didn't fall halfway down. We lost 1. In the last part of the trip, it's moving faster, so there's even more air resistance, right? And it's going further distance, going faster. If you say you lose 1 block here, you're not really being consistent. Give me something reasonable. That's all I ask. You could say 2, 3, anything but 1 or 0, right? So I'm just going to make it 2 because it's simpler to work with. So we got minus E dis. And we're losing them, so I'm drawing them below. And then I'll put my equals sign. Is everybody good? Now what are you saying we're going to end up with, please? How many in EG? Why 1? So let me get this straight. You want to do more work and have the numbers come out the same as someone who did less work? Remember that blue line you could move anywhere you want? You remember that? This is actually key that you see this. People usually want to make the 0 EG where? They usually make this on the floor, center of the earth, sea level, places like that. Does this need to be anywhere in particular, this blue line? If you put it in a clever location, your problem will be simpler. What are you guys proposing as the simplest? At the lowest height, so at the minimum height. So basically, is this blue line going to be exactly on the ground? Is it on the ground? It's not on the ground. Most physics students have no idea what they're really solving for. They think they've solved for the velocity when this thing actually hit the ground. It's not. What this is that's the velocity at the moment just before impact. And the 0 EG, this is our 0 EG height. Are you guys good? And who gets to choose that? So take advantage of it. It'll make your life easier. Okay? So what's EG? What's the elastic? Now, imagine, how many blocks does EK have to be? Okay, when you're counting blocks as we are here, it's not that hard. If this line were lower and you had one block here, and it's not wrong. But when we use the equations, what will happen is, if you have a block here still, that means you have to solve for it using an equation again. Do you understand how much harder that is? You guys cool? It's a whole other term you have to incorporate in your equation. So always make the minimum height your 0 EG height. Does it mean the Earth is not pulling at that height? How about everybody? Does it mean there's no gravity field at that height? Okay, go. Okay, let me check. -2. 4 plus 1 is 5, -2. Yeah, dude. Well, you're awesome. You are a champion. You guys said 4. You meant what? Cool. Everybody good? Cool bananas? So you see how it works, right? I suppose you should probably try number 2 right now. I'll have you present your whiteboards in about 7 minutes.